Hi, this is a continuation of buckling, and we are looking at extension of Euler's formula. So we have condition number 3 now. And for this case is one fixed n and one pin n. So like what you see over here. So one n is fixed, right? So you don't allow rotation at point B. So this is what we call fixed. And this n is what we call pin. It's allowed to rotate. It's only restricted from the x direction. It can still move in the y direction. That's why the y direction is an arrow or on a roller. So over here, that's where LE is equal to 0.7 L. So based on the condition we have before, we have 0.7 L over radius of gyration, and this will be 88.86. Okay, so the L over R is equal to 88.86 divided by 0.7 is equal to 127.9 or 126.9. So when that's the case, again, I focus on this diagram over here, right? So this we will see a shift on when we have to use we have to apply for buckling analysis, right? So as you can see from here, so now we have been to 126, so a new line, right? So 126, I'm going to eyeball this, it's about here. Alright, so this is our 126 line. So this is 126.9. So you can see what does this mean. I'm going to sketch this graph. We'll go like this, so you can do stress equal force divided by area. Then so over here you have to do a buckling analysis or design based on buckling analysis. Okay, and the last condition, which is what you see over here. So condition number 4. Right, where both ends are fixed. Now this is a bit confusing. Okay, this is a bit confusing over here. When they consider both ends are fixed, they are not considering the overall length. Okay, sorry, it's not so they are so for this case, you can see that they restrict rotation in both direction. So both ends are fixed, right? So what does this mean? Is the equivalent length now is equal to 0.5 L. And then if we put the formula in, divided by slender ratio, this is still 88.86. So what you get over here, your L over R is equal to 177.7. So what this means, back to this diagram over here, right? You can delay the buckling analysis until you have reached a value of 177. Okay, so we'll be somewhere around here, right? So at this point is where you have 177.7. Then you need to do buckling the design will be based on buckling analysis when both ends are fixed. Okay, so you have to get it clear when it's fixed and when it's pinned. Okay, so let's look at one example now. So as you can see on this example, let me move. You have a structure. There's an I-beam, right? There's an I-beam. So the structure can, but before we go on, let's look at, so we have a length of 6 meters. So what we have from here to here, right, we have a length of 6 meters. Okay, so for example, from here to here, we have a length coming 6 meters. We have a centric load coming down from the top. So we got a centric load coming down from the top, and this centric load is at 16 times 10 to the power 3. Alright, so we're going to find the critical load. Okay, we're going to find what is our critical load. Okay, to calculate the factor of safety, which is equal to the critical load divided by the applied. Okay, so our P applied for this case, you know, is 16 times 10 to the power 3 Newton. Okay, so we have to find how, okay, we have to draw for ourselves how the structure, this there, by the way, there's a cross-sectional area, so how the structure will buckle. Okay, so we're going to sketch this out. So if we now view our structure now in the YZ, sorry, we watch in the XZ plane. Okay, so XZ plane. So now we have our X and Z. And then this is rotation in the y-axis. So I'm going to sketch this out now. So this the structure. So when we view from X and Z, so this is how our structure look like, right? And then we have our hidden detail. Okay, so we have right. So that is our, the centerpiece is our web. Okay, our web. So the structure now can deform, right? It can basically deform in this direction. Okay. So we also know if it deform in that direction, so is rotating. Okay, we know that this is rotating. Right, there's a rotation, or it's not a good name known as rotation, but bending curvature is about the y-axis, right? Or the rotation, if you can call it, yeah, rotation is about the y-axis. So this is the curvature, and this is how our structure is bending. Or you can see our structure is bending this way, right? So we have now to so if bending curvature is about the y-axis, for this case we have to find Iyy, right? So why Iyy? So remember the formula, recall that stress in the z direction can be equal to my over what? The moment rotation about the y-axis multiplied by x plus by mx over ixx multiplied by y. So we are considering Iyy because the rotation is about the y-axis. So if you look at bending moment, we can also say that for this case, our moment is also rotating in about what? The y-axis. Okay, so we know that for this case, the I has to be what? Iyy. Why this is critical? Because if we look at the critical load, will be equal to pi squared over L squared multiplied by EI, right? And we know E, everything is constant. I is your variable now, depending on how the structure is deforming. Okay. Now, if we look at the other buckling direction, so there's another possibility that it will buckle in the YZ plane. Okay, so it will buckle in the YZ plane. Okay, so now I'm going to draw a YZ plane. So when you view this structure on a YZ plane, this is what we will see. Oh, no more hidden feature. It's a straight. Right. Then these are your flange. Okay. So for this case, if this is our centroid or neutral axis, now the structure, so we also know that this is rotation about x. So the structure can deform this way now. Okay, now both ends, for this case, we are going to declare both ends are pin. It's allowed to rotate. Oh, pin, I should not have drawn that for pin. Okay, so both ends are pin. Right, so both ends are pin. And in fact, I make a very easy error while drawing this. I will redraw it. So when the load is being pushed down, the structure will also deform in this direction. Okay, so this is how the structure is bending. Okay, so likewise for this case, it'll be bending this way, or you'll be deforming this way under buckling. Right, so the radius, the curvature is the same, right? That's how it's going to curve. So for this case, if it's going to buckle this way, so the bending curvature is about the x-axis. So for this case, we have to find Ixx. Okay. So from calculation, I'm not going to show this, okay? I'm not going to show. So we find that Ixx is equal to 7.752 times 10 to the power minus 6 meter 4. And we also found that Iyy is equal to 0.819 times 10 to the power minus 6 meter 4. Okay, so which one will buckle first is Iyy. The lower value will buckle first because the lower value means it's lower resistance to bending. Okay, so we're going to select Iyy value as the resistance to bending is lower. Okay, so we know that PCR, we're going to calculate critical load now. So PCR will be equal to pi squared over LE squared E multiplied by Iyy, right? So the critical load, so pi squared divided by the equivalent load. So now both ends are what? Both ends are pinned. So you look at your condition. When are one end pinned, both ends fixed, and then we come back here. Both ends are pinned. The LE is equal to L. Okay. So we know that LE is equal to L. Okay, so L is equal to 6 meters. Squared. Young's modulus, I'm going to take it as for steel. And Y is 0.819 times 10 to the power minus 6. So from here, your critical load is equal to 44.906 times 10 to the power 3 Newton. So what this means is that this structure can, based on its design, it can withstand a load of 44.9 kilonewton. Okay, so that's what it means over here. Okay, 44.9 kilonewton. So therefore, finally, the factor of safety, okay, to calculate based on whether it will buckle or not. So this will be equal to 44.906 times 10 to the power 3 divided by 16 times 10 to the power 3. So this is equal to 2.81. Okay, so that is our safety of factor based on our structure that we have calculated. So what we have learned down here for today is it's critical to know what is our slender ratio, our L over R, and also down here, this example is when to use IXX or Iyy. It all dependent on the bending curvature. Like for this case, it's about the y-axis, right? So you look at Iyy. For this case, the bending or the curvature is about the x-axis. We're going to use IXX. Okay, that's all for now. Thank you.